Welcome back to Physics 141 Online. In this part of the course we've been talking about heat engines and specifically how to calculate their efficiencies. And there's a special kind of heat engine that we can describe that has the maximum possible efficiency. And this goes back to some work that was done several hundred years ago by a French engineer, a young man named Carnot. He figured out the kind of process on a thermodynamic cycle that has the maximum possible efficiency. And it's got the characteristic that all of the processes involved in the cycle are what we now call reversible. And for us to understand how Carnot did this work, we need to think a little bit about what processes are irreversible in nature. Irreversible means that although they might happen in one direction, you could never turn around and have the same thing happen in reverse. And so one example is friction converting mechanical energy completely into heat. Okay, that can happen in one direction, but we can never completely convert heat into mechanical energy, and that's just something that we observe in nature. Secondly, and this one should be pretty familiar to us, heat will never get transferred from a cold object to a hot object. It always goes from the hot to the cold. And so it won't happen in reverse. And finally, a process where the working substance, for example, a gas inside some sort of piston cylinder, does not remain in equilibrium throughout the process. If the volume changes very rapidly, then the gas does not stay in equilibrium. The pressure in the gas is not the same everywhere inside the container. And as a result, then if you tried to reverse that process, it would simply not happen the same way that it did in the first direction. So these kinds of processes are irreversible. We just never see the opposite of them happening in nature. So we want to avoid these kinds of processes if we want to construct a heat engine that has the maximum possible efficiency. And so what does that mean? That means that a reversible engine, the one that has the maximum possible efficiency, must have no frictional losses. And so, of course, we do the very best that we can to lubricate mechanical parts that are going to rub across one another. Also, all heat transfers must occur isothermally, right? We don't want heat to go from a hot object to a cold object because that's an irreversible process. We'd like to have heat exchanged between the environment and the engine when they're at the same temperature. And finally, the working substance must remain in equilibrium throughout, which means that all these processes must occur quasi-statically. A quasi-static process is also a reversible process. And it's impossible to meet these conditions exactly in the real world. However, we can approximate this behavior and we can come up with a theoretical cycle on a PV diagram that will be a truly reversible cycle, and it will give us the maximum possible efficiency that we could ever have under ideal conditions in the real world. So it's a little bit like the ideal gas. The ideal gas isn't exactly the way that any gas behaves in nature, but it's an approximation that they all roughly obey in a particular limit where the gas is very dilute. And so the Carnot engine, the efficiency that we're going to derive for the Carnot engine, will be the maximum possible efficiency that you can have if you could get rid of all of the irreversible processes. And so it will allow us to have a benchmark that we can use when we calculate the efficiency of a real-world engine where not all of the processes in the cycle are truly reversible. So what does the Carnot engine look like on a PV diagram? The key is actually number 2 here. All heat transfers must occur isothermally. So we want a process where the heat comes in when the temperature is not changing, and when the heat is released, that it's released where the temperature is not changing. So we need 2 isothermal steps in our cycle. And it's pretty easy to see how that works if we just construct a PV diagram, imagining the system starts at step 1, or at state 1, and expands isothermally to state 2. And under these conditions, heat is flowing in. It's isothermal, so delta U is not changing. That means that Q is equal to W, and so Q is actually coming in. Q is equal to negative W, I'm sorry. And so Q is coming in. It's being absorbed by the gas during that step from 1 to 2. Then, and this is kind of neat, we can get a further expansion, which means that the gas is doing a little bit more work on the environment by having process 2 to 3 be adiabatic. And adiabatic is nice from the standpoint of efficiency because there's no heat absorbed and we're still doing some work. So from 2 to 3, that gives us the rest of the useful work that the gas is doing on its environment. Now we have to get back to state 1 because we want this engine truly to be an engine, which means it has to be cyclic. It has to be able to occur over and over again. So from 3 to 4, we're going to compress the gas, again, isothermally. So the process from 3 to 4 is a piece of an isotherm at a lower temperature than the process from 1 to 2. And then from 4 back to 1, if that compression is done adiabatically, it's going up to a higher temperature than it started at state 4, and it goes back to step 1. And so again, there's no heat released. So the heat comes in the step from 1 to 2. Work is done from 1 to 2 and then 2 to 3, and then heat is released from 3 to 4. And then finally the system returns to the original state. So remember that T1 and T2 are the same, and we'll call that TH because that's the high temperature, and that will represent the temperature of the reservoir from which the heat is coming in. And then T3 and T4 are the same because that's also an isothermal step, and we will set those equal to the temperature Tc, the temperature of the cold reservoir, because that's the temperature at which the heat is released from the gas. And so, going back to the definition of efficiency, if we can calculate the net work that's done by the gas in that cycle and divide by Q absorbed, we'll get the answer that we want. W is equal to the difference between the heat absorbed and the heat released, divided by, then, to get the efficiency, the heat that's absorbed. Because in this ideal process here, heat was only absorbed from 1 to 2, and then it was released from 3 to 4, and there were no other heat terms in the problem. So simplifying this expression, QH over QH is 1, QC over QH is just QC over QH. So in order to find the efficiency of this ideal kind of engine, the Carnot engine, all we need to find are the two heat expressions. And that's really not that difficult. It's done in the textbook, and so you can follow through the work in the textbook. And it turns out for this kind of process that QC over QH is equal to TC over TH. The ratio of the heat released to the heat absorbed is actually equal to the ratio of the two temperatures. And so as a result, the Carnot efficiency becomes 1 minus Tc over Th, or the difference between the two temperatures over the high temperature reservoir temperature. So this is the maximum possible efficiency for a heat engine that operates between these two temperatures. Most of the time in the real world, we won't approach this. We'll get an efficiency that's less than this. But the point is that this result is the maximum possible efficiency we can get. We can never have an efficiency of 1. Now, if you look at this expression, you can think of things you can do to make this efficiency as large as possible. You can make TH much, much greater than TC, because that will make the numerator really, really large. But no matter how large you make it, it can never be any larger than the denominator. It can't even be as large as the denominator, and so the Carnot efficiency is always going to be less than 1. So, one caveat, these temperatures, because of the use of the ideal gas law in calculating the ratio of the heats that gives us the temperature ratio here, these temperatures have to be in Kelvin. So be careful when you plug numbers into an expression like this. So let's do a quick example. All right, a heat engine absorbs 500 kilojoules of heat from a reservoir at 2000 Kelvin and releases 200 kilojoules to a reservoir at 300 Kelvin. So we've got a high temperature and a low temperature reservoir. Heat is absorbed from the high temperature reservoir, and some of it is released to the low temperature reservoir. How does the efficiency of this engine, which is an example of a real engine, how does that compare to an ideal engine? The best possible efficiency you could have for an engine operating between 2000 and 300 Kelvin. So it's a very simple calculation. The efficiency is the work done over the heat absorbed, and that's QH over minus QC over QH. We're given those numbers, so 500 kilojoules comes in, right? 200 kilojoules is released, so the difference between the two, which is 300, that's how much work is done. 300 over 500 is 3/5 or 0.6. So that is the actual efficiency of this particular engine. Now the Carnot efficiency, and we'll label this differently because it's an upper limit, that would be 1 minus the ratio of the two temperatures. And so here we get an answer, when we plug those temperatures in, of 0.85. And let's be clear, when we compare these two numbers, the difference between 0.6 and 0.85 is due to the practical kinds of factors that occur in the real world. We've got friction, we've got heat losses. We can't make an engine that's actually completely reversible. All right. In principle, we can improve that efficiency by trying to reduce some of the factors that cause these non-ideal losses. However, the difference between 0.85, the Carnot efficiency, and the hypothetical upper limit of 1, that's a fundamental limitation of nature. Whenever you have two reservoirs at 2,000 and 300 Kelvin, you will always have this upper limit on how efficient of an engine you could actually build. And so that fundamental limitation is not due to practical matters like friction. It's just because that's the way nature is. And we enshrine that property in what we call the second law of thermodynamics. We've already talked about that just a bit in class. This fleshes it out, thinking about efficiencies of heat engines, so you can see the effect of the second law, and also, in this case, the effect of real losses, like frictional losses. So, I hope this is a good introduction to the Carnot engine. We'll do some more discussion of this and examples in class, and that's where I'll see you.